Welcome back, class. So at this point, I want to sort of summarize where we are in our development of atomic theory and what we understand about the atom, and highlight again some of the major points along the way that we've been discussing. So to sort of start at the end, right? So by 1932, with the discovery of the neutron, we had a pretty complete picture of what was going on with the basic structure of the atom and how we visualized it. Now, that does not mean it hasn't changed since then, but the basic ideas were pretty much there at that point. And so, to sort of highlight the major points along the way, we started out with Dalton's atomic theory, and then we moved to J.J. Thomson's experiments with the cathode ray and the development of the Plum pudding model, right? So remember, this was around let's see here, this is around 1896 when he did his cathode ray experiments. Whereas Dalton got us all started in the early 1800s with his development of his first theory. Now, as we moved on from there, we had the Plum pudding model. Millikan comes along about 1909 and gives us the fundamental charge of an electron. So he sort of completes Thomson's work in discovering the electron, whereas Thomson could come up with the mass-to-charge ratio of these tiny particles. Millikan was able to sort of complete the idea with coming up with the fundamental charge and therefore the fundamental mass of the electron. Now, something we haven't really talked about, but going along around this same time was about 1897-ish, into the early 1900s, Marie Curie and others, Rutherford and a guy named Becquerel, were all working on the discovery of what we know as radioactivity. Now, we're not going to focus very much in this course on radioactivity or radioactive decay. We do dedicate a chapter at the end of Chemistry 2, right? So if you were to go on and take the second semester, at the end of that, we do dedicate some time to talking about radioactivity. But along this time, Rutherford and Curie and others were discovering radioactivity of elements and characterizing some of these particles and or rays that are given off by these radioactive elements. So alpha particles and beta particles and gamma rays. Right? Now, we point this out because, of course, in his gold foil experiment a few years later, right, Rutherford utilizes alpha particles. And so all of these areas of research and this discovery is sort of coming together to help us understand the atom, giving us a tool to sort of probe the structure of the atom by using these radioactive decay particles. In 1911, right now we have the nuclear model of the atom, right, which along with, gives us the nucleus, and protons, right? So at this point, we have the nucleus, we have the electrons around the nucleus, we have these positive protons within the nucleus, and then a few years later, right, Chadwick sort of completes the picture, sort of solving one of the last fundamental questions about atomic structure, and that is, where does the missing mass come from, right? So there's questions about how, the mass of one element is different from another element, and but the number of protons is not enough to account for this mass difference, come in solved by the presence of another fundamental particle, the neutron, which of course is neutral and has no charge. And this is one of the reasons why it was so difficult to discover, because most of the tools that were used to look at these things looked at what made it fairly easy to discover charged particles, but not neutral particles. So by 1932, we had the protons and the neutrons in the nucleus, the electrons outside the nucleus, sort of our modern atomic structure that we think about today. Now, there were more advancements to atomic theory, and these are mostly centered around the behavior of the electrons. Right? At this point, the nucleus is pretty much set from what we understand about it, and frankly, the nucleus doesn't do a whole lot, especially in the study of chemistry, unless we start talking about nuclear chemistry or reactions of the nucleus, which again you won't do until next semester. Right? Chemical reactions, the nucleus is just along for the ride. Right? It doesn't really get involved. All of the interesting chemistry happens with the electrons, and so further models that were developed, principally the Bohr model. Not too long after all of this, not too long after Rutherford's work, and then later Einstein and others' work on quantum mechanical models in the late 20s, early 1930s, gave us more insight on how the electrons exist within an atom. Now, we won't discuss these theories until much later on in the course, around Chapter 8, when we start delving a little more closely into the electrons. So now that we have this picture, let's take a closer look at these three fundamental subatomic particles that make up the atom. Now, if you look in this table, which just comes out of your book, we have listed the mass of these three particles and the charge of these three particles. Now, one thing you'll come to learn is that unless we're doing very specific types of calculations, which we don't typically do in this course, we don't really need to know what the actual mass and the actual charge of these particles are. What we really want to know is the relative charge and the relative mass. So, what we've done is we've assigned the particles a relative mass based on something called an atomic mass unit. And the atomic mass unit was simply a developed unit, right? It was defined as 1/12 the mass of a carbon atom with 6 protons and 6 neutrons. Or what we'll later refer to as carbon 12. And so what we can see is that this mass units are based on carbon 12. And so now what comes out of that is, if you do this, that we get the mass of a proton and a neutron are right around 1 AMU, and an electron is much, much, much smaller. So if we look at the actual mass numbers, we can see, that the electron contributes almost no mass relative to the protons and neutrons to the mass of the atom, right? And this is why we can say that, the vast majority of the mass of the atom is located in the nucleus. Now, we also do the same thing with charge. So, we know that the charge of a proton and the charge of the electron are of equal magnitude, but simply opposite signs. So, protons being positive, electrons being negative. Now, we don't need to worry about these exact charges, right? All we need to understand is that one proton neutralizes one electron in terms of charge. And so we assign a proton a relative charge of positive 1, an electron a relative charge of negative 1. So within an atom, right, if I need equal numbers of protons, and electrons give a neutral atom. So in your neutral atoms, you're going to have equal protons and electrons. And of course, the neutron, having no charge, has a relative charge of 0. So now we have a little better understanding, hopefully, of the basic fundamental properties and how we're going to talk about them when we look at describing the atoms.